Hello, in this video we're going to go over Fischer projections as well as the importance of those enantiomers we were talking about. So we've already looked at a few Fischer projections, but they depict three-dimensional shapes for chiral molecules in a two-dimensional way. So the chiral carbon will be represented by the intersection of two lines, a vertical line and a horizontal line. So down below we have L-glyceraldehyde on the left and D-glyceraldehyde on the right. So we saw these before. And you can see the three-dimensional figure on the top, and then the two-dimensional figure is on the bottom. And that's the Fischer projection, the two-dimensional figure. So you'll notice we have two lines, a vertical and a horizontal line, and the chiral carbon is right at the intersection point. And then the aldehyde will be on the top, CH2OH will always be on the bottom, and then we can depict whether the OH group is on the left or the right. So for L-glyceraldehyde, OH is on the left. For D-glyceraldehyde, OH is on the right. So again, in Fischer projections of carbohydrates, the carbonyl group, so the aldehyde or the ketone, will always be at the top. So the reason we do that is it should be projecting away from us, kind of similar to our three-dimensional drawing. Notice that the aldehyde's kind of pointing away. That's also true for CH2OH. That should be kind of pointing away from us. The hydroxyl group, or the hydroxyl group towards the bottom is also really important. This is how we determine whether we have an L version or a D version of our carbohydrate. So in order to figure out if you have the D version or the L version, what you'll do is find your aldehyde or ketone at the top, then go to the second to last carbon. So this will be the last chiral carbon. Then you're going to look at the OH group. If the OH group is on the right-hand side, then you have the D version of your carbohydrate. If the OH group is on the left-hand side, then you have the L version of your sugar. So L equals left, D equals right. And remember to find that second to last carbon on the chain and look at its OH group. Okay, so the physical properties of D and L enantiomers, or carbohydrates in this case, are generally the same. However, D and L enantiomers can rotate polarized light in equal but opposite directions. So this is really cool. Compounds can rotate light. And if you have the D version, that's going to rotate light in a different direction than the L version. So for instance, down below we have a figure of a polarimeter, and we can use this polarimeter to determine how much a molecule can rotate light. So ordinary light, natural light, can kind of come at you from all angles. So ordinary light vibrates in all planes, so all directions. But what we can do is pass this through a polarized lens. And that polarized lens is going to force light to travel in one direction. So here we have light going up and down. So we'll say that this is at 0 degrees. Then we're going to pass this polarized light through a tube that contains our enantiomer. So let's say it's D-glyceraldehyde, for example. Then at the end we'll have a detector that will tell us how far the light rotated. So if we started at 0 degrees, maybe it moved over 5 degrees. So that would tell us that D-glyceraldehyde rotates light 5 degrees to the right. What that also tells us is that L-glyceraldehyde rotates light 5 degrees to the left, so equal but opposite directions. Now, this polarized lens that I mentioned is really similar to polarized lenses in sunglasses. So if you have a pair of sunglasses with polarized lenses, what's going on is that light that's reflected from a surface is traveling in all directions. So it's kind of messy and it can create a glare. But polarized lenses are only going to let light travel through at one specific direction, and all the rest is kind of pushed away, essentially. So that can help cut down on glare when you're driving, for example, or if you're at a body of water. So those are really useful. Okay, so back to enantiomer properties. The enantiomer that will rotate polarized light to the left is called the levorotatory enantiomer. We can also symbolize this as a negative sign in parentheses. The enantiomer that rotates light to the right is the dextrorotatory or positive enantiomer. So this is sort of where D and L come from for our designations, but unfortunately not all D carbohydrates rotate light to the right, and not all L carbohydrates rotate light to the left, so D and L don't necessarily correspond with right and left, but this is just to demonstrate that these enantiomers do have differences in their physical properties, so they're not exactly the same. Now down below we have D-glucose and L-glucose. So again, D-glucose will rotate light in one direction, L-glucose will rotate light in a different direction. But the main way that we can tell whether something's D or L is again by looking at that second to last carbon and determining if the OH group is on the right or if it's on the left. If it's on the right, you have the D version. If it's on the left, you have the L version. So this property of rotating the plane of polarized light is called optical activity. So molecules with this property are said to be optically active. So that tells us that enantiomers are optically active because we have a D version and an L version. So we can actually measure optical activity to help us differentiate between enantiomers. So down below I have another example of enantiomers, D-fructose and L-fructose. So fructose actually has a ketone at the top instead of an aldehyde. And again, we just look at that second to last carbon on the bottom there to figure out if we have the D version or the L version. So D-fructose has its OH group on the right, L-fructose has its OH group on the left. So why do we care? Why is this important? Well, in some instances, only the D or L enantiomers are found in nature. If both forms are found in nature, they're rarely found together in the same biological system. So as an example, carbohydrates we just saw are chiral, but also amino acids are chiral, and those are really important for creating proteins in biological systems. Now, humans can only metabolize the D isomers of monosaccharides. So D-glucose, D-glyceraldehyde, D-fructose. And most animals are only able to utilize the L isomers of amino acids to synthesize proteins. So we can't use the D isomers in that case. So these are really important the enantiomers are really important to understand because we can only utilize either the D isomers or the L isomers depending on the type of molecule. So a real life example, in the late 1950s, thalidomide was an anti-nausea medication that was prescribed to pregnant women, but it was found pretty quickly that it was causing birth defects. So scientists went back to the drawing board to figure out what was going on, and they found that there were actually two enantiomers of thalidomide. There was the right-handed version, which they called R, and then the left-handed version, which they called S. So just this tiny difference in the stereochemistry, or the three-dimensional arrangement of atoms, caused these birth defects. So one of these was actually useful as an anti-nausea medication, but the other one was highly toxic. And this was a huge issue. It took a while actually for pharmaceutical companies to stop selling this drug or using this drug, which was really unfortunate. If you want to read more about it, I put a link with a Science Daily article down below. It's a short article, but you could also just look up thalidomide, and there are plenty of resources about this drug and the issues that it caused. So again, it might seem arbitrary, but the right-handed versus left-handed types of molecules do matter. They can have really positive or really negative effects. Okay, so next time we're going to talk about how to further classify sugars or carbohydrates and some of their physical properties as well. So I will see you then.